Hello, in this section we're going to talk about continuity over an interval. So in the previous section we talked about continuity at a point. Now we're going to talk about continuity on an interval. So our learning outcomes: define continuity on an interval, state the theorem for limits of composition of functions, and provide an example of the intermediate value theorem. So as we look into this, talking about continuity over intervals, so a function f of x is said to be continuous from the right at a if the limit as x approaches a from the right of f of x equals f of a, and it's said to be continuous from the left if the limit as x approaches a from the left of f of x equals f of a. So that is going to give us continuity from the left and the right for a certain point in an interval. So a function is continuous over an open interval if it's continuous at every point in the interval. And that's one of the things we're going to look at here is maybe it's not continuous everywhere, but we can identify the intervals over which it is continuous. So state the intervals, if there's more than one, over which the function is continuous. So if we were to factor that denominator, this becomes our f of x is x minus 1 over x times x plus 2. Nothing's going to reduce out, so we don't have a removable discontinuity. But we would have, so that each denominator equal to 0, so x equals 0, x plus 2 equals 0 means x equals negative 2. So that means that this is continuous everywhere except 0 and negative 2. So it's going to go from negative infinity to negative 2, now with parentheses of course, negative 2 to 0, and then 0 to infinity. And if you're not used to these U symbols, that means union. That means we're joining those three in fact now, but we're joining these different intervals with the union. So what this is saying is it's continuous everywhere except at negative 2 and 0, and this is how we write it symbolically. Okay, let's look at the next one. State the intervals over which the function f of x equals the square root of 4 minus x squared is continuous. So with a radical, the stuff inside the radical, that 4 minus x squared has to be greater than or equal to 0. 2 minus x times 2 plus x is greater than or equal to 0. And if we look at each of these, we'd have 2 minus x is 0, so 2 equals x. 2 plus x is 0, so 2 equals negative x, or x equals negative 2. And I do this, trying to find those intervals on which it's going to be satisfying this inequality. So we know we have zeros at negative 2 and 2, so we could graph it or we can do this chart. And I'm surprised to see a lot of my students seem to like this chart versus graphing. So I think it's easier for this situation to do the chart. So we get a value smaller than negative 2, we'll call it negative 3. Between negative 2 and 2, 0. Bigger than 2, we'll go with positive 3. And then if I plug the negative 3 in here, 2 minus negative 3 is positive. 2 plus negative 3 is negative. A positive times negative is a negative. Put a 0 in there. 2 minus 0 is positive. 2 plus 0 is positive. A positive times a positive is positive. Put the 3 in there. 2 minus 3 is negative. 2 plus 3 is positive. A negative times a positive is a negative. And we're looking for the places it's going to be positive, so we would look at within this interval here. So the solution is negative 2 to 2 would satisfy this. So this is continuous over the interval negative 2 to 2. Okay. Moving on. State the intervals over which the function f of x equals the square root of x plus 3 is continuous. So again, we have a radical. X plus 3 must be greater than or equal to 0. So x is greater than or equal to negative 3. So it'll be negative 3 to infinity. That's it. Same thing here. I determine the set of x values where the square root of 13 minus 11x is continuous using interval notation. So I think we're going to have a set of check marks down here. No, we don't. Okay, so we have 13 minus 11x needs to be greater than or equal to 0. Stuff under the radical has to be greater than or equal to 0 because that's an even index. So 13 minus 11x, or I should say 13 equals or is greater than or equal to 11x. Divide by 11. So that 13 elevenths needs to be greater than or equal to x. Or you could say x is less than or equal to 13 elevenths. So it's going to go from negative infinity up to 13 elevenths. And I use this squared off bracket because it can be equal to 13 elevenths. You can be 0 under a square root, but you can't be negative. Composite function theorem, this is one of those outcomes. If f of x is continuous at L and the limit as x approaches a of g of x is L, then the limit as x approaches a of f of g of x is f of the limit of g of x as x approaches a, which is f of L. And there's a video for you to watch. If you'd like to watch the video, go into the lesson. So evaluate the limit as x approaches pi over 2 of cosine of x minus pi over 2. This would become the limit. Let me back that up. This would become cosine of the limit as x approaches pi over 2 of x minus pi over 2. So this becomes cosine of, well, that limit's going to be pi over 2 minus pi over 2, which is cosine of 0, which is 1. Likewise for this one down here with the sine, that's going to become sine of the limit of, as x approaches pi, sorry about that, of x minus pi. So that becomes sine of pi minus pi, or sine of 0, which is 0. So we have continuity of trigonometric functions. The trigonometric functions are continuous over their entire domains, and that sounds possibly a little like, how can we state that? But they are continuous over their domains, and so you have to think where their domains don't exist. Now, sine and cosine are going to be for every place. Sine and cosine are continuous everywhere. But tangent and secant are not continuous at pi over 2 plus n pi. So like pi over 2, 3 pi over 2, negative pi over 2. And then you have your cotangent and cosecant, excuse me, are not continuous at pi plus n pi. And this is because like tangent and secant have cosine in the denominator, and cosine is 0 at pi over 2 plus n pi. And then where n is a natural number, so or integer, it's just the integer because it could be negative or positive or negative whole number. And then cotangent and cosecant have sine in the denominator, and sine is 0 at multiples of pi. Integer multiples of pi. Okay, moving along. There's a fun-filled proof if you'd like to delve into that. Now, another thing is the intermediate value theorem, and this is something we actually covered in Math 126 for my classes, and so hopefully it's not too new for some people. Let f be continuous over a closed interval bounded by ab if z is any real number between f of a and f of b. So that's when you plugged it into the function f, z falls between those, then there's a number c within that interval. Remember, f is continuous. Number c in the interval from a to b such that f of c equals z, and there's a nice graphic here. So c here falls between a and b, and then z falls between f of a and f of b. So show that f of x equals x minus cosine of x has at least one 0. So we want to find a place where it's going to be negative and a place where it's going to be positive. So if we can show we have a number below and then above the x-axis, then we must have a 0, because this is a continuous function. X is continuous, cosine of x is continuous, so this is continuous. We don't have any holes here, or asymptotes for that matter. So let's look at this. What if we had f of 0? That's going to be 0 minus cosine of 0, and that's going to be 0 minus 1, so it's negative 1, which, guess what, is less than 0. Then f of pi over 2 is going to be pi over 2 minus cosine of pi over 2, which is pi over 2 minus, and cosine of pi over 2 is 0, so it's pi over 2, which is positive. So by the theorem, there must exist a value between 0 and pi over 2 such that f of the call value, they called it c, f of c is equal to 0. And if you ask where I got 0 and pi over 2, you just start trying different values. And I know that 0 is meaningful to cosine and pi over 2 is meaningful to cosine, so those are two to work with that helped us come up with each side of the x-axis. Okay. When can you apply the intermediate value theorem? So if f of x is continuous over 0, 2, and f of 0 is positive and f of 2 is positive, can we use the intermediate value theorem to conclude that f has no zeros? The answer is no. It doesn't work that way. What it does is it guarantees a 0 between two values if you have one side below 0 and the other is above 0 if it's continuous. But it doesn't say there's no zeros, because it could dip down and come back up again. Here's another fun-filled video for you. And here's another one. It says f of x equals 1 over x. F of negative 1 equals negative 1, which is less than 0, and f of 1 is 1, which is greater than 0. Can we conclude that f of x has a 0? And the answer here is no, because f of x is not continuous over the interval from negative 1 to 1. At 0, it has an infinite discontinuity. And I believe this, oh, I've got two more. Show that f of x equals x cubed minus x squared minus 3x plus 1 has a 0 over the interval 0 to 1. So f of 0 is going to be 0 cubed minus 0 squared minus 3 times 0 plus 1, which is 1, which is positive. and f of 1 equals 1 cubed minus 1 squared minus 3 times 1 plus 1, which is, I believe, negative 1. Let's see here. It's 1 minus 1, 0, minus 3 plus what's negative 2, which is less than 0. So there is a C. I'm going to do this math notation. That means in the interval is an element of the interval from 0 to 1 such that f of C equals 0. Okay, now we're on to what I think is the last one. Suppose that f of x is a continuous function with f of 1 equals negative 1, f of 5 equals 1. Determine which of the choice is the best statement for any y in the interval from negative 1 to 1. And so they're telling us it's continuous. F of x equals y for some x in the interval from 1 to 5. And the answer is always true. Okay, and that's it.